Hello everyone, welcome to my talk. The title of our paper is MQH Locality Sensitive Hashing on Multi-Level Quantization Errors for Point to Hyperplane Distances. I want to give a brief introduction of this work from the following four parts. First, I will talk about the background of this problem to be solved because the point to hyperplane distance studied in this paper may not be used as frequently as a common point-to-point distance in practice. I will also talk about our motivation for the design of such a new index structure in part 1. In the second part, I will give some detail of the proposed structure, including a brief introduction of the workflow and some technical results. The experimental results will be discussed in part 3. The definition of P2HNS is that given a dataset consisting of points and a query hyperplane in a high-dimensional Euclidean space, we hope to find the approximate nearest point of the query hyperplane. More formally, if we use H to denote a hyperplane with such an expression, solving P2HNS is equivalent to solving a minimization function. Here x denotes an arbitrary data point in the dataset. Finding nearest points to the query hyperplane has some real applications, such as active learning with support vector machine, maximum margin clustering, and large margin dimension reduction. For example, in the first application, the active learning iteration process selects those unlabeled points closest to the hyperplane into the training dataset and retrains the classifier with the new data. During this process, we need to solve the P2HNS problem. Apparently, an exhaustive search is not acceptable for a large-scale dataset, which requires us to design an efficient index structure. At the first glance, the only difference between P2HNS and ANS, that is the proximate nearest neighbor search, is the query type, but the designs of their index structures are quite different. For example, the graph-based methods which are widely used in solving ANS problem cannot be directly used for this problem because in some bad cases, the query hyperplane can intersect with lots of Voronoi cells, such that the determination of the next hop in the graph-based search is difficult. So in this paper, we use other techniques to solve this problem. First, I want to briefly introduce locality sensitive hashing, which is the basis of the proposed structure. We call function family locality sensitive hash function family if the following two conditions are satisfied. The first condition says that if two vectors are close, their hash values are likely to be equal. The second condition says that if two vectors are far away from each other, their hash values are likely to be different. In practice, we can design a suitable hash function family based on the used metric, and we usually need multiple hash functions to strengthen this result. Currently, there have existed some LHH-based methods which can solve the P2HNS problem, such as NH and FH. Their basic idea is to map the data into a Euclidean space with higher dimension and transform P2HNS to ANS or AFNS in the new space. Then we can use existing LHH structures to solve the problem. Next, I want to talk about the motivation in this paper. One of the most important advantages of LHH is that it can provide a strict probability guarantee on the query results because of using random projection. But this also makes the precision level of LHH relatively low in the comparison with other learning-based techniques, such as vector quantization. So it is natural to raise a question: is it possible to improve the performance of LHH by incorporating the idea of vector quantization? Of course, we still hope the proposed structure can offer some probability guarantees. In this paper, we make the following two contributions. First, we propose an index structure to achieve this goal. Second, we focus on how and when to combine these two types of codes, that is the hash code and the quantization code. This page shows a brief overview of the workflow of a proposed method. Our index structure works on a vector quantization technique called RQ, that is a residue quantization. Its basic idea is that for each vector, we can generate its subcode on the first level. Then we can compute the residue vector based on the generated vector on this level. We feed the residue vector into the second level and repeat this process. If we concatenate the subcodes on all levels, we actually obtain an approximate vector of the original data point. Of course, if we use more levels, we can obtain we can get a longer code with the expense of more time to tackle such a code. Here we can raise two questions for RQ. How do we determine the length of code reasonably, and is it necessary to generate a code with the same length? It's hard to answer these two questions for the original RQ, but if we introduce the idea of LSH, we can answer them. From the workflow of the proposed method on the right-hand side, we can see that compared with RQ, we need to additionally compute the hash code of the residue vector on each level. In the query phase, we tackle each point level by level. If the hash code on some level satisfies our termination condition determined beforehand, we can judge that this point is not the nearest neighbor with a high probability. Otherwise, we will go deeper until reaching the last level. In this way, we can check less bits to exclude those far neighbors and check those possible nearest neighbors carefully. Of course, the key here is how to set the termination condition. Here is a geometric illustration shows how the termination condition works. In figure A, suppose that H is a query hyperplane and X is not the nearest neighbor, but it is not far away from H. We quantize X to X hat 1, X hat 2, and X hat 3 on the first, second, and third levels respectively. On each level, we can compute the hash bucket and the hash value of each data point. We can see that the size of hash bucket decreases as the level goes deeper. On the first and the second levels, the hash value of X hat 1 and X hat 2 fall inside the hash bucket, which means that we cannot treat this point as a false point on these two levels. On the third level, we can judge that X is a false point with a high probability guarantee because the hash value of X hat 3 falls outside the hash bucket marked in green. If a point can pass collision testings on all levels, this point is regarded as a candidate. For real datasets, the number of candidates is quite small, which will be shown in the experiments later. The indexing phase of MQH is simple. As discussed earlier, we first generate the code by quantization and then generate the hash code based on the residue vector. Because vector quantization is a learning-based technique, it is suitable for the distributions of real datasets. On the other hand, theoretically, LSH is most suitable for random distribution because of random projection. Generally, the distribution of real datasets is very different from the random distribution, but the distribution of the residue vector after quantization is much closer to the random distribution, which also suggests applying LSH to these residue vectors. The query phase of MQH is slightly complicated because we need to introduce several conditions to determine if a data point can be pruned during the examination process. In this algorithm, steps from 12 to 15 are core steps, which give such conditions. Here, WLX is an internal parameter regarding data point X, whose definition is shown in step 6. RLX denotes the norm of the residue vector on level L. Additionally, we use a user-specified parameter flag to represent two variants of MQH. If flag is equal to 1, the algorithm has a strict probability guarantee on the query results. If flag is equal to 0, the algorithm has a weaker probability guarantee which needs some assumptions, but it works faster with a fairly high precision level. Another critical user-specified parameter is delta, shown in step 12. It takes value in the interval between 0 and 1. If the delta is large, the data point can pass the collision testing more easily, which means that we need to check more candidates and the query accuracy is comparatively low in this case. On the contrary, if the delta is small, we can put more data points on upper levels, which makes the algorithm run faster with some loss of accuracy. Delta is recommended to take a value in the interval between 0.3 and 0.5. A detailed analysis on its setting will be discussed later. Next, I want to briefly introduce some theoretical results supporting the design of the proposed algorithm. For the ease of comprehension, I will focus on explaining the implication of each result and skip some detail of the notations. The used hash function is almost the same with the used for the cosine distance. Here, alpha denotes a vector drawn randomly from the random distribution, and x tilde denotes the residual vector of x. Based on such hash function family, we can use the result in lemma 1 to characterize the hash values of those data points close to the hyperplane. On the other hand, we can use the result in lemma 2 to characterize the hash values of those data points far away from the query hyperplane. Then by using lemma 3, we can characterize the collision numbers of closed points, which determines the collision testing. Next, I want to talk about some results related to the multi-level structure. Lemma 4 shows the relationship between the quantization error and the bucket size. We can see that by a careful setting of parameters, we can ensure that the hash bucket on the deep level definitely contains the hash bucket on the upper level. This shows that as the level goes deeper, passing the collision testing becomes more difficult because those points for outside the hash bucket will be pruned immediately. Finally, theorem 1 gives the results on the probability guarantee of the algorithm in the query phase. For the complexity of the proposed algorithm, we list all results on this page. The time complexity in the query phase needs some attention. Here we introduce two parameters, alpha and beta, where alpha times L means the average terminal level of data points. Beta times n denotes the number of candidates, which require exact distance calculation. For the random distribution, the value of beta is computable. For real datasets, beta is very small and is generally smaller than 0.01, which will be shown in the experiments later. Next, about the experimental results, we used 5 real datasets and 4 benchmark methods. We mainly focus on the comparison with FH and NH because they are state-of-the-art ones. We consider two forms of datasets, original dataset and the dataset after normalization, both of which have some applications in practice. This page shows the results on normalized datasets. We can see that MQH has the best performance on all datasets. For the original datasets, MQH still works best. Here I omit the dataset deep because deep itself is a normalized dataset. As for the index size shown in the table below, because MQH requires less hash functions than the other compared methods, its size is smallest. On the other hand, MQH requires more indexing time than the other two methods because of using residue quantization. On this page, from the table above, we can see that as the level goes deeper, less data points can pass the collision testing. On the other hand, from the figures below, we can see that such multi-level structure works better than a straightforward combination of VQ and hashing. Finally, I want to talk about the setting of a critical parameter delta. From the theoretical results, which are shown in the two figures on the right-hand side, delta has a significant effect on the query accuracy when it is in the interval 0.3 and 0.5, which is almost consistent with the results of real datasets on the left-hand side. In summary, we propose a multi-level structure to solve the P2HNS problem. Experimental results show that the proposed method performs better than the state-of-the-art LSH-based methods. In the future, we will consider applying this structure to other metrics. That's all. Thank you.